Thank you, Dr. Rao, for a spirited talk about this nanotechnology. Open for questions? Yeah. First, Dr. Muradian, and then you can.
What type of energy use this nanomotor? Electric energy?
No. It is in space. You know, what the laser beam, it is in space. It's just rotating, rod is rotating. The laser beam is holding in space.
Chemical energy?
No chemical. It is actually what is happening is, in this particular, we think it is asymmetry in the nanorod that makes the interaction with the laser beam and the dielectric rotate it. So you have a very smooth cylindrical rod, it doesn't rotate well. You have a slight asymmetry. That may be the cause of this rotation.
Is there angular momentum in the laser beam?
Yes.
Is it polarized?
Yes, I think.
Dr. Gray.
You mentioned these metals have become non-metallic.
First question, is it linked to a change of a structure?
Oh, sure.
Sure. It becomes amorphous, for example?
No, not that structure. Electronic structure.
Okay.
Electronic structure.
Yes. And second question, are there some non-metals which become metallic?
No. It is opposite, is not known. Because, you know, what happens is that you make things smaller and smaller, they approach an atom or a molecule, the energy levels become more and more localized. So as you decrease the size, you'll always, a metal become non-metal, the opposite won't happen. Yes.
Dr. Arber?
What is the present state of risk assessment of applying nanosciences in our civilization?
Well, there's a lot of work. As I said, I didn't have time to talk about the toxicology, and a lot of work being done on toxicology associated with nanoparticles. For example, people are using nanotubes without really understanding whether it has any bad effect. So I'm against people using nanotubes in all kinds of biological applications. One has to be careful. So what is being done now is we are substituting those nanomaterials which have these toxic elements by non-toxic material. For example, cadmium peroxide is good for something. Cadmium is not good. So can I do the same thing with zinc peroxide, which is harmless? So people are trying to do that. But where graphene scores, graphene, unlike carbon nanotubes, doesn't seem to be carcinogenic. Particularly if you functionalize graphene, there are three major papers that have come now for tamoxifen, many of these cancer drugs, for delivering them. Graphene seems to be very, very good, unlike nanotube, which I would not recommend. So there's a lot of concern about the toxicology, and that much more work is yet to be done, and a lot of work has been done, in fact.
I want to follow up on that. This is a concern I have. One of the major sources of climate change, at least regionally, is the similar graphitic particles,
Sure.
or soot, sizes between 10 to 100 nanometers. We now know they're melting the Arctic sea ice. We know they're melting the Himalayan glaciers. Is anyone looking into if it is massively used? Ultimately, they all have to escape to the atmosphere, one form.
I told you, I'm waiting for samples of your carbon. I think in my lab would be the best, and myself and my friend Ajay Sood maybe, we can study Raman spectroscopy, whatever you want. And I'm waiting for a sample of that carbon to look at whether, what kind of, is it graphene or the nanotube? I don't know what is in that carbon there. I think it would be very nice to do that. I hope you can send me some.
No, after listening to your talk, it's my highest priority to send our filters to you. Thank you.
Okay, sure. You've already taken some microscope?
Yeah, we have.
I've not seen those, yeah. Sure.
When you talk about applications of graphene, one wonders if it's possible to prepare larger amounts of this graphene.
We can make several grams of it now.
How is it made?
Oh yeah, in chemical, that is all by chemical means. But if you do it by a Scotch tape technique, to make 1 gram, it costs $30,000. So exactly, out of question. So the physicist method won't work. We have to use chemistry, and we can make reasonably good graphene in large quantities now.
And these are freestanding films?
Oh, no, you see, no. You see, single layer graphene can never be kept by itself, because as soon as you remove it, it forms graphite. So either you have to disperse it in a liquid medium or put it on a solid substrate. So what we therefore do is maybe 2-layer or 3-layer graphene, I can put it in a bottle, no problem. So for most applications, bilayer or tri-layer graphene is as good as single layer in many applications, many uses. So that I can give in large quantity. Single layer graphene, I'll have to put it in liquid or something like that.
So you showed us these beautiful pictures about mercury clusters, and it's intriguing that you start off with, say, one atom of mercury. This is a pretty simple, even a cluster of a few mercury atoms is fairly simple. Then it becomes rather complex, since we're talking about complexity. And then at something on the order of 300 atoms, it becomes simple in a certain sense. That is,
Absolutely.
it becomes a metal, which is a relatively simple a system. And so it seems as if, perhaps contrary to intuition, but I think quite common in the physical world, that as we go from a single atom to a lot of atoms, that we get an increasing complexity. And then when we go more, we get simplicity again. And I was wondering whether you had any insights. I mean, I don't think this is universal, but it's quite common.
No, it is very common. It's probably universal when it comes to this. You have an atomic regime, then you have a 2, 3, up to 13 atoms, say. It is like a molecule. It's a molecular level, like you can use molecular orbitals to explain them. So you have 50 or 100 atoms. It's more of a cluster. It's not simple molecule, bit different. You've got bands that don't have bands. Then neither are the electron levels localized. But when you come to 200 atoms, you get plasma and resonance. 200 atoms will show you plasma and resonance as if collective oscillation of electrons, just like in a regular metal. So you see these differences, whether it is nickel or gold or mercury. It's a very universal thing. I think, unfortunately, people who work on 3 atoms of gold, like my friend Uzi Landman in Georgia Tech, who does a lot of calculation, he calls it cluster. I said, okay, 3, 4 atoms is a molecule. The levels will be bonding, it will be like a molecule. So I think there are 3, 4 regimes, like you said, where the electronic structure would change.
Well, so I'm wondering, is this universal behavior? Both you and I have talked about high-temperature superconductors. In a certain sense, the behavior of high-temperature superconductors is quite simple. The understanding of why it happens seems to be beyond our ability, at least at the moment. But if we just think about the properties of a system, do you think this is a universal situation, that going from small numbers that are simple to sort of mesoscale,
Right.
which is complex, to macro scale, which is simple again? Is that a universal behavior? Can you think of...
metals, yes, I think it is. Because what seems to be happening is you have atoms, then you have molecules, then the magic number packing will start. 13, 55, 147, 561, the magic numbers. And their cohesive energies, and they all become important, but they're still not bulk metal. But above 500,000 atoms, it becomes bulk metal with regular bands. So we know the changes in packing and structure, electronic structure, but I think that is universal enough in metals.
Metals. So what about other materials there?
Well, you can't do these things with other non-metals so easily. But people have done, my very good friends who are, the theoreticians have done in zinc sulfide, oxides, a lot of calculations. They seem to be very similar. 3 zinc sulfide, like Richard Catlow in London has calculated 3 or 4 zinc sulfide or things like that. They are like molecules. They give unique structures which are different from the zinc blende or some other structure of the crystal. Some unique structures will be formed at small number of clusters. So this is known in such simple compounds.
Why would you like to call a complex a cluster of, let us say, 100 atoms? It's just unusual, but it's well understood. I mean, there is no complexity, I think, in such a complex. It's different from the normal metal. But is it complex? I don't think so.
Well, you see, the question is the properties. Professor Ertel is an expert in this. You know what is amazing? Gold becomes very reactive. it becomes a catalyst, it does oxidation of carbon monoxide. Similarly, nickel, small particles become very chemically reactive. Carbon monoxide is absorbed on nickel very nicely. A lot of work has been done. When you take a small cluster of nickel, it splits carbon monoxide into carbon and oxygen atoms. So the reactivity is different, the electronic structure is different. So they're not the same material. No, they're not the same.
They are different.
Yeah.
Thank you, Dr. Rao. I have one idea, just listening to all this and seeing how this could really penetrate into energy generation and computers. And we also know any particle less than a micron could become airborne and stay for weeks to months. Whether the academy should be thinking about holding a meeting on this new technology.
In fact, I was going to suggest in the evening, I think nanoscience and technology in service of humanity, something like that would be a very, very good topic.
Service of humanity
or a symposium or something like that.
and consider the environmental and health effects
Yeah,
so
sure,
that maybe
sure.
the technology could be guided.
There's a
in
lot of
different-
interest in this, yes. Yes.
Thank you.